ITRL, Integrated Transport Research Lab, and to the seminar series we usually do during springtime. And I would also like to welcome the ones who are on Facebook watching us live, so welcome. And then everyone in here knows that we are also broadcasting live on Facebook today. And today the talks will be from one of our own, I would say, Maria, who's been doing work at ITRL, and she's soon about to finish her PhD. Mm-hmm. And today we will learn a little bit more on what happens when you cut the cord. I guess the cord is the fossil fuel line, maybe, of buses. Mm-hmm. We will see. So I will not stand here and talk much more than that. I would just like to welcome Maria and also give you a little bit of hint of coming seminars. So we have 3 more. 8th of May we will have Maria Xylia from Linköping University talking about green logistics. And then we will have 22nd of May Carolina Isaksson, Jakob Witzell, Malin Henriksson talking about smart mobility policy. And then the 5th of June we will have results from our master thesis that we have here at KTH. So please go into the website if you found those 3 of interest and register for those. I give the floor to you.
Thank you, Mikael. Good morning, everybody. It's really cool that I get to do this seminar today. I joined the Transport Lab in the end of 2015, and I remember that I had a seminar in April 2016 where I would present the concept of this project and how we're planning to deal with it. And it's very cool to think that 2 years later so much has happened, and I'm here to show you today some experiences we got from that project, some comparison between what we have now in terms of technologies for charging electric buses, and also some outlook for how to scale up the solutions related to fossil-free and electrified bus transport. So as Mikael said, I'm about to finish my PhD thesis quite soon. I'm associated with the Energy and Climate Studies unit. I have been working there under the supervision of Professor Silveira and the Transport Lab, but now I have left KTH and I'm working at Sweco as an energy systems analyst for the past couple of months. And I'm going to start with some of the basics and what we're dealing with. We're discussing about electric buses. So regarding the powertrain, we have 2 options: either battery electric bus, which is fully electric, just a motor for an electric motor for operating the bus, or electric hybrid solutions where we have both a battery and an electric motor and an internal combustion engine to help with some extra range when we don't have sufficient capacity from the electric operation. In my research and the projects we did, we dealt mostly with battery electric, although the bus we tested in Södertälje was an electric hybrid. Regarding the energy storage solutions, we have the ultracapacitors, which is a bit of a different technology that is now being tested. The batteries, as I said, that operate most of the electric buses, and fuel cells that work on hydrogen. My research focused on battery buses because they are mostly commercial at the moment. For some cases they are gaining momentum. Most of the manufacturers are producing electric battery buses. The fuel cells might be coming in the future, but it was not my research. Charging technologies, we have 2 options. First, it's the conductive technology, the plug-in. You can see here the example from Roopsten here in Stockholm. We have a mast, and there is actually a connection between the bus and the charging infrastructure for delivering the electricity. And we also have the inductive, otherwise known as wireless, which was what we tested with the Scania bus in Södertälje. There is much less infrastructure being visible, as you can see. Most of things are happening underground, and the transfer of energy is happening with induction through magnetic coils. I will talk about that a bit more later. And then depending on the charging technology and the kind of operation we have also different strategies, charging strategies. We can have slow charging, overnight or depot charging as it's called, which is happening under lower effects, lower power. So that takes a bit more time to do, but it's healthier for the battery. It doesn't put the battery under too much stress. And we also have the fast charging, which is happening under higher effects, power effects. It takes significantly less time, and it's what we choose when we have charging at the stop or charging along the route of the bus. One note here, because I think that sometimes we get to miss that, is that even though we have fast charging as a solution, and this is what most of research now is on how to reduce these times and make these buses more efficient with fast charging, we will always have slow charging, regardless of whether you have opportunity or fast charging or maybe electric road systems or anything. The buses or any vehicle need to charge slow at the depot, at the parking or anything, just to balance the battery. So that is not going away probably. And to evaluate a bit the charging alternatives that we have in place and their benefits and drawbacks related to the strategies that I discussed now, I have this table here that compares the cost for infrastructure, for the batteries and operation, for slow overnight charging, for fast charging that is stationary at the stop, and for dynamic fast charging, which is the electric road system as we would call it. So when it comes to infrastructure, when we're talking about the slow charging, the depot charging, we don't have so many infrastructure costs. It's a cheaper infrastructure installation, but we have higher vehicle battery costs and higher operation costs. And that happens because for operating throughout the day and managing to not charge at all for some hours, you need a quite big battery, which costs, of course. And operation-wise, when we talk about buses, if these buses need to go back for any reason to the depot to charge throughout the day, they need to stay there for at least a couple of hours, which means that we need some extra buses and some extra driver's time to replace those buses that need to charge. When we talk about fast charging, we have more higher infrastructure costs because the fast chargers cost quite a lot, the connections to the grid cost quite a lot. We talk about high power transfer, net electricity grid tariffs, and so on and so forth. But we have comparatively decreased battery costs. We use much smaller batteries than the slow charged buses, and again we have decreased operation costs for the charging time that is needed. The best solution in terms of operation costs and battery costs would be to have a dynamic charging, a non-electric road system, because then you wouldn't need to save time for the charging, the drivers wouldn't need to stop to charge, you wouldn't need very big batteries, you would need quite small batteries actually, just to save some energy in case there is some lack of electricity along the road, but on the other hand it would cost quite a lot in terms of infrastructure. So these are the pros and cons of its solution, depending on the operation and the goals that you have in place as you get different bus solutions. So different solutions, as I said, and depending on the local context, have been testing around Europe. I would like to mention the Zero Emission Urban Bus System, ZEUS initiative in Europe, which gave quite a lot of funding in different European cities around, I don't know, almost all of the EU countries, to test electric buses, fuel cell buses, or buses that are generally low emission or even zero emission buses. We have core demos in 9 countries, but many other small demonstrations happening. Our project in Södertälje was funded by the Swedish Energy Agency, but the project in Ropsten, Line 73, was funded through the ZEUS program here in Stockholm. So these are what is happening around Europe and the different projects, and we have also some Nordic demonstrations, more specifically. This table is not fully updated to 2018. I would put a lot of boxes here all over the place in different cities of Sweden that test actually electric buses, but what I can say is that we mostly see conductive charging happening, the blue boxes. The one with the pantograph system. The bus in Södertälje that we tested was the only wireless charged bus that we have in the Nordic region, which was a first and one of the first in Europe, which was very interesting to see, especially when we're talking about how the bus would perform in the weather that we have here. we can see also between the different cities of the Nordic region that different battery sizes, different bus manufacturers are active, different charging systems and charging infrastructure manufacturers are involved. So there is a lot of diversity and a lot of different things being tested. Which brings me to presenting our project, our Södertälje, and what have we learned from that specific project. So that was line 755 from Södertälje seed to the Tomtits Experiment Museum. The line was about 10 kilometers long, and there was one charger installed, one wireless charger at the Tomtits Museum. So the one charger on the one end stop of the bus route was enough to charge for the full route. And our aim with this project was to implement, test and evaluate the potential that wireless charging may have for buses when we talk about city traffic, in order to reduce emissions, to improve energy efficiency and decrease the fossil fuel dependence that buses have through the use of electricity. And that, as I mentioned, was funded by the Energy Agency, Swedish Energy Agency, for the research part of it. And it was a collaboration between Scania, SL, the Public Transport Authority of Stockholm, the municipality of Södertälje, Vattenfall, and of course the Transport Lab and KTH. So the bus looked a bit like this. It was a normal 12-meter bus that had a hybrid operation, so it had a combustion engine to help the electric motor. It had some batteries installed of about 60 kilowatt hours and inductive charging with effects, nominal effects of 200 kilowatts. The charging was delivered by Bombardier and it was fitted to the Scania bus. And here I would like to show you how the charging system looks like with some info that comes from Scania, Vattenfall and Bombardier. So we have the bus, and as I said, wireless charging works through magnetic induction. So we need to have two magnetic coils. One is underground, the primary coil here, and one is mounted on the bus, the secondary coil. Through the pickup, this secondary coil goes closer as the bus parks, and then we have the exchange of energy through the magnetic fields, as I mentioned. The additional infrastructure that is in place, as I said, it's not very visible, but we still need the cooling tower, of course, for cooling the coils, and also an electricity box, an Elskop, for the connections and the high power transfer. Some converters as well, from AC to DC and from DC to DC on the bus. So this is basically the solution. The most important thing to remember is the primary coil that is buried underground, and it's a huge metal slab that weighs quite a few tons, if I remember correctly, and the secondary coil that is mounted on the bus. Then, as part of the operation, which started in mid-2017, I think, the operation started. So we collected some data from that operation in order to analyze what happened in terms of, in relation to the project goals. And I analyzed about 50 dates that were given to me with data on the energy consumption, on the share of its mode on the bus, of the weather conditions, the battery conditions. And what we saw was that we had about share of hybrid operation of on average 25%, which means 75% of the operation of the bus was fully electric, if we want to see it from the positive side. There are days actually that there is almost no hybrid operation, like it's almost zero, so the bus was going on full electricity at these times. The difference in the shares between different days relates to a variety of factors. It can be that the charge was not fully completed when the driver parked, so not all of the energy was transferred. It can be that there was more energy, higher energy consumption because of a specific driving style that can lead to higher energy consumption. It can be many factors, so we expect variations, but in general the results of the hybrid versus electric mode operation were quite okay for the demonstration, I would say, but not as high as set in the beginning of the project. So by evaluating the energy efficiency of the bus, we see that the calculated values from the operation are in line with what we've seen in existing literature and other projects that have actually tested the operation of electric buses. And when we have full electric operation, the days that we had zero share of hybrid, they were particularly positive, I would say, when it comes to the consumption of the bus. But of course, this share of 25% of hybrid operation would be key to improve and reduce so that we can fully exploit the energy efficiency benefits of the electric bus. An additional factor that most of the people talking about the bus projects and demonstrations of electric buses do not talk that much is that still we have heaters that are not operating on electricity. We don't use, there are very few cases where an heat pump is used, for example, for the bus. We still use some biodiesel fueled small motor just to run the heating system. That should be a future step to fully disengage from fossil fuels in bus transport, but it will take some technological improvements and R&D. And finally, the battery operation was in general stable. We saw very good temperatures for the battery. In general, the stabler the battery temperature is around some specific values, the more efficient is the battery management system, which is key for improving the battery health and the life cycle of the battery, because you do not get infinite use. You need to change at some point. The better you have used the battery and the better your battery management system was, and the better your charging strategy was, the longer the lifetime of the battery would be. So let's relate the project goals to what we had as a result. So there were 4 main project goals that were reported in the beginning of the project. First was to follow up and document the whole implementation process, which is quite important because we are still at the demonstration phase, and discussing how the actors were involved, how the project went through, and what were the key steps taken along the way is also a very important result, I think, and it was a very good idea to put it as a goal. And that was documented, and it was submitted, and it's a publicly available report on how the implementation went. The second goal was the 60% decrease of the energy consumption, where we're talking about per kilometer, in comparison to conventional buses. And the project, from the measurements we took, can show a 60% lower energy consumption per vehicle kilometer when we compare to biodiesel buses. If we talk about comparison to gas-powered buses, we would talk about an even further reduction of about 70% compared to them, because gas buses are not as energy efficient as diesel buses. Then the other goal was the high accessibility and robustness, 90% of the system. The accessibility was not as high as the set goal. It was still more than 50%. There were some issues that had to be solved since it was a demonstration, and there is nothing more to do than just test the solution in real operating conditions. So there were some issues when we are discussing about mixing 2 different technologies and 2 different manufacturers. And of course, the conditions that we had during winter have been a challenge, such as salt and snow and cold weather. So that has been something that needs to be improved in the future for commercializing that technology. The last goal related to behavioral aspects, to show that the bus drivers appreciate the system and they trust the system, at least as much as a conventional system, and potentially even more. There were surveys that were performed both with the drivers and some of the passengers, and there was overall a higher rate of appreciation of the system, of the electric bus, compared to a conventional bus, mostly because of the lower noise. That is quite nice if you're working in that environment for 8 hours driving the bus, to not have so much noise from your engine. Other positive comments were about the fact that it's environmentally friendly because it's going on electricity, and people were aware of that, both drivers and passengers. But there were some negative comments on errors because the bus was a prototype, or it was a bit tougher for some drivers to manage to charge as they should. So both plus and minuses there in the evaluation. But as I said, it was a great testing project, and it was something that was tested for the first time in these conditions. And what was also novel was the collaboration of the actors that were involved. It was a broad project between both public actors, academia, private actors in the industry, which was what was quite unique in that case. Then I will have to go to the next section of my presentation, which is taking it a bit further and trying to understand how wireless charging compares to other options that we have, and what are the benefits and drawbacks of its solution that we have in place. So during this project, I was trying to look into different experiences that stakeholders have within different projects, mainly in the Nordic region. We did a survey discussing that, comparing these technologies and understanding what are the drivers that stakeholders have in participating in such demonstration projects. And the survey was quite diverse in the people that responded. So we had public transport authorities, had the largest share, but we also had municipalities, manufacturers, academics, transport operators, and charging manufacturers that replied to that survey. It was mostly people coming from Nordic countries and a little bit, and a small share people coming from other countries, as you can see there, only an 8%. 68 of these respondents have been part of organizations that have experience of more than 3 years with electric bus demonstration projects. And out of the about 50 or 60 people that I sent the survey to, we had about 40% response rate, which is quite good in anonymous surveys, I would say. So we got about 25 responses. And analyzing these results, we got to plot the advantages and disadvantages of conducting charging, as I said, with a pantograph. So the main advantages that the respondents found was the reliability and the maturity of the technology. It has been tested more than any other charging technology that is now available on the market, so the respondents think that it's more mature and ready to be used. Among the disadvantages, we see the bus dwell time and the reliability, which I find a bit contradicting because it's also an advantage to some respondents and a disadvantage to others. Probably, for me, it probably means that some projects worked great and some projects did not work as they were expected. Or that when we are comparing reliability, we do not compare the available charging technologies with each other, but we compare them to the conventional diesel or gas buses. It can be both. But it's also the bus dwell time that is considered a disadvantage with this technology because, as I said, you need to stop, wait to charge. It can be some minutes. If you're charging slow, it can be very long. So that is a problem for some of the respondents. When we come to the wireless charging, there were not as many answers because there are not so many people that are testing wireless chargers. I'm still showing the results, but I have to say that it's very few answers. But what we got there as the best advantage was that we don't have cables and moving parts. And that is actually what is one of the biggest advantages of wireless charging, because it can both be good for the whole visual of the solution, the charging solution. You will see very little because there is no movement, no visible things. But it's also very good from a practical perspective that you will not have to maintain that infrastructure that much because you don't see that much of it and it's not exposed to cold weather or other conditions. So that can be a benefit compared to the conductive charging that has moving parts that will need maintenance along the way. And it's very unclear how much this maintenance costs at the moment, actually. The disadvantage among the few responses that we got on the wireless charging was that there are high costs associated with it. It's a less advanced technology than conductive. It's still at the testing phase, so it will cost more. But through time, we see that both charging technologies, both wireless and conductive, have been showing decreasing costs. And it was also interesting to ask these respondents about their perception of these projects, the demonstration projects, and if they plan for continuing. And the first question that is related to that is how did this demo affect the perceptions that the respondents had on electric buses? And 58% of them says that they're more positive now compared to before starting the project, which is a good sign. There is a 40% that says that their perceptions have not changed, but there was no follow-up question actually there to see if they have not changed from positive or negative. But they have not changed, so the project did not affect them at all. And also if there are plans to continue operating these electric buses after the end of the demo project. 68% in the survey replied yes, and a smaller percentage replied that they don't know, and potentially yes, but they're not sure. of course, I would say that we see here a lot of positive momentum and people want to continue participating in this kind of projects. What was unclear from the survey responses and from what I see overall is that it's not very clear who will actually be responsible for the continuation. So most of the people are positive on continuing, but not many of them or stakeholders are willing at this point to take the lead in that. So we will see how this evolves when we go beyond demonstration projects. And also what motivates this participation in the projects. The first that comes in the number of responses was to gain experience with the new technology, of course, test new things, and to increase the environmental sustainability of the bus. Another interesting response is to increase the collaboration between stakeholders. So projects like the one we did in Södertälje is very important in that perspective, to get to know the different stakeholders that are part of a completely transforming public transport sector. We have different actors and players in the market now. And another interesting insight from the surveys was on the unexpected problems of the implementation. And I was expecting to see the costs first or getting longer time than needed. These questions, these answers are there, but the one that got the most responses was that it's hard to compromise stakeholders' perspectives, which I think is very interesting from expansion point of view. If we need to solve the problem of upscaling to fossil-free alternatives and new technologies as electric buses, we need to find a way to collaborate better and compromise the different perspectives in this new field. All of these responses from the survey, I took and analyzed them in under a methodology called thematic analysis on understanding the charging challenges that we have in place, comparing the technologies and what are the biggest trends that we see in what the perceptions are at the moment. So I have identified four main categories. The first is the technology maturity. So most of the choices are based on what is considered to be technologically mature, on what is tested basically in a proximity. So what is tested in the regions and neighboring countries and neighboring regions of Europe is being what is continuously implemented, and people trust to that maturity of the technologies. Another issue that is very important is the cost effectiveness of the technology and how the total cost of ownership of the bus is affected by the charging technology that will be chosen. Will I get increased operation costs? Will I get increased maintenance costs? How will it be with the scheduling of the driving, the scheduling of the drivers, the scheduling of the routes themselves? So this is one challenge that is very important and needs to be solved. Another issue is the compatibility. So most of the charging technology choices are not actually happening because they are locked to a specific bus. So there is a bit of a problem on how we can manage to make the charging systems compatible. And in the cars, the private cars, this has been solved by having standards, charging standards in place that are not so common in the bus world, but hopefully will be, so that we can manage to charge different buses with different charging systems and different solutions. And the last challenge is the charging efficiency, which is not so much the efficiency of transferring the energy or how high is the efficiency grade of the technology itself, but how fast will the charge happen, under which power effects will this happen. So the higher the power that we can transfer, the shorter the charge. So that is very important in the fast charging aspect that we're discussing here. So that was what the charging technologies are about and what are the challenges we have ahead. And I will close the presentation with how to scale up from these demonstrations that I've described to something bigger. So the demonstrations that we have in place are quite simple. We have one bus, probably 2 buses maximum, and there is one route. The stations are very clear and specified, so it's quite easy to decide on where to place the infrastructure and what infrastructure you will use. The question becomes a bit more complicated if we have multiple buses crossing routes with each other, having common spots, having common stops along the way. And the problem becomes even more complicated if we are having real systems, like the one of Stockholm, which has 500 routes, 500 bus routes, and about 11,000 bus stops. So where do you choose where you will electrify if you want to scale up from demonstration, and where do you choose to install your charging infrastructure if you want to put fast chargers in the city? So that was the question that was in place, and beyond the demonstration project in Södertälje was something that was part of my PhD, to understand how we can manage to offer a solution for placing charging infrastructure in an optimal way in the city of Stockholm, with the potential to do it in other cities as well. So I developed a model that optimizes the total costs or the total energy of the bus system. So we have two different scenarios, and it takes into account the costs, such as the cost for the charger, the cost for the buses, the cost of the fuel, the cost of the operation and the maintenance. The technological aspects, if we have a conductive or an inductive charger, if we have biodiesel, if we have electricity, if we have biogas. The capacity of the bus for the battery, if it's a big battery, if it's a smaller battery, what battery. And the emissions that its fuel and its electricity option has in place. And lastly, some design aspects were part of the model, such as the distances between all of the stations that I showed you in the map of Stockholm before, the trips per its, the daily trips per its line, the length of the line, and the schedule of these buses. So the model was structured from the data collection part on the technologies, the costs, and the schedules. That was simple programming so that we can prepare the data for being implemented into ArcGIS, which is a geographical information system that was used for the maps and the distance matrices. And then that was put into an optimization model, which is called GAMS, and we optimized on the costs of the system and the energy, as I mentioned earlier. And then with these three components in place, you can do quite a lot. You can do sensitivity analysis on the charger networks. You can look into different cost levels. You can look into the distribution, spatial distribution of the chargers in the city, and so on and so forth. So some of the results, for example, here we have the optimization of the total costs, and that is an output that comes from processing in the model. It's a map of these bus routes that I mentioned before. And you see that some of them are electric, the blue ones, some of them are biodiesel still, the red ones, and we have some charging spots, mostly within the inner city. And this happens because the model tends to choose bus stops that would share the charging infrastructure with multiple routes. So it's better to have some location that is a big hub, transportation hub, like a subway station. The infrastructure there will be there forever, permanent, so you will not probably see extra stations, bus stops moving from there in the future, so you can put your charger without worrying. And you have the multiple bus routes crossing because they take you to the subway stations and everything. So that's a lucrative location, so this is why most of them are here. And the distances, of course, are shorter. As you can see, there is a dense network being built. That I will talk a bit more about, I think, about the inner city later. And what we see there is that we have 42 routes that are being electrified out of this 500 that I said, using 59 chargers. So the optimal solution is not electrifying the network 100%. The optimal solution is to choosing the routes that are best for electrifying and choosing the routes that are best for biodiesel or biogas or any other option you have in place. And that led to energy consumption that reduced about 30% compared to a reference system that would be using 100% biodiesel in place, and a reduction of about 40% in emissions because of the use of electricity. Yes, I should talk about the costs. I haven't marked them. The costs were approximately the same as what we would see for the reference system, and that is something that I think is very key in the findings of this model, because what we have to spend on infrastructure for the vehicles and the charger and all of the infrastructure investments is actually balanced out by the fuel cost savings, because electricity is much cheaper. So yes, moving now to the charging time analysis. Of course, this is an issue. If we talk about pure feasibility aspects and the distances between stops along a route, you might be able to electrify, but you don't want to spend a lot of time because that will increase both your operational costs and it will increase the waiting time for the passengers. You want to charge as fast as possible and go as far as possible to your next stop. So the next step in the analysis was to look very closely into the inner city, where we have this opportunity that I discussed about the large transport hubs and the smaller distances along the routes of the buses. So what we see there is out of the 21 routes that are crossing the inner city, 10 of them are electrified in the model. Again, not all of them. There are some that go across the suburbs that are not electrified and are not optimal for electrification. So these 10 routes, we analyzed the charging time required for this. And we found out that it was 3.5 minutes, the average charging time for these locations, with a very small standard deviation. So I would think that from a time perspective, it is totally feasible to electrify the inner city, and you would not need much infrastructure, just some chargers that could electrify larger shares of the network. So these are some examples of what can be done with this optimization model and the approach of behind it, on how to actually think big when we discuss electrification and shifting from demonstrations to something that is more actual. I will close with some remarks on how to choose the locations for the charger. It's some work we've been doing now at my new job, but has been part of what we've discussed also in the Södertälje project. So it has some experience from how we discussed the location of the charger there. And I would divide it in 5 categories: spatial requirements, integration, expansion, operation, and special cases. So the spatial requirements relate to how many chargers we have and how much space we have for parking the bus, for driving the bus to charge, for having different buses coming into the same location. For installing the equipment. If it is conductive, you install the mast, the pantograph, and other cooling systems and electricity systems. If it's wireless, you just do the cooling tower and you dig and everything. So you need to be aware of the space you have and if it is available for installation. Then integration. Do we have electricity in the area and under what effects? Do we have pipes passing underground, for example, district heating on some other pipes? You cannot dig there or install things on top of them. What is the width of your sidewalks? And even if you have trees that need to be moved, which was something that was actually part of our project in Södertälje, to move a tree before the charger was put in place. Then the expansion, mostly about sharing infrastructure between multiple routes, about being able to have adequate grid capacity on spot for charging multiple buses under high power. And the operation, how the drivers will operate and have their brakes and everything during that operation of the bus. And special cases, if you need to think about snow, if you need to think about cultural sensitive environments and everything, how would you discuss installing the infrastructure? How would it visually be and how would it be perceived? So some conclusions or remarks, I would say. Despite that we're having many studies that are dealing with electric bus performance and understanding the energy consumption, the design of the system, we have very little focus given on charging infrastructure. It's usually taken as granted. Conductive charging, as I said, is dominating in the Nordic region. It's considered a more mature technology and it's currently cheaper. So this has been an advantage. But there are more aspects defining the charging technology that is chosen than just costs. It can be the bus technology that is in place, if we have lock-ins to that, the reliability, how much time it takes to charge, how it operates under winter conditions, how is the visual impact, many factors. It's not just a cost issue. Unexpected issues, as I said, very interesting finding of this research was that there are a lot of challenges related to the collaboration between stakeholders and the planning of the processes, the projects. So we need more experience, more projects happening, and more lessons learned actually to become better, because practice makes perfect, after all. We have generally perceptions that are positive from the operation and the demonstrations. The stakeholders are willing to continue in this way, which is good. But shifting from demonstrations to upscaling will be a question, I think, of infrastructure placement and of smartly using what is in place and what should be in place. So these are some remarks, some references here. Most of the things that I've showed now are based on work which is published under these 4 scientific papers. 2 of them are already available, 2 are under review. They're all part of my PhD thesis, which will be defended on the 16th of May at 1 o'clock here at E2. Little advertising in the end. But you're all welcome. I'm discussing how we can upscale electrification, some of the things related to the model, the charging technologies, and an outlook for the future. So thank you very much for listening. Thanks. Questions?
We can start with, we have some questions from the webcast.
Aha.
So we can start with them and then we take.
We have questions from the webcast.
Yes.
Wow.
The first one is about, I read it like it is. The pros and cons around the charging alternatives shown seem to only consider today's world with human drivers. What about tomorrow's world where buses and other vehicles will be self-driving? Do you still believe that dynamic charging is the best solution, and why?
I always get that question when I'm presenting at the transport lab. I remember this is always the first question about autonomous vehicles. I think that we should not link the charging technologies and the electrification to autonomous vehicles. It's nice to have it together, but it's 2 different concepts. If it happens, we manage to integrate those 2. I would say that, of course, the biggest impact for public transport would be that you would not need to worry about driver costs and operation costs, which are actually the largest share of the costs that you have now for having a bus system in place. It's more than 60%. So that would be giving more solutions when it comes to the available time that you will have to charge without worrying. So you might see probably switching towards slower modes and fast charging will not be necessary. But on the other hand, you will have to have more vehicles in place for doing that. So that would give you some extra cost there, which might still be balanced by the lower driver costs, I would guess. The issue that needs to be very, very much addressed in the case of autonomous vehicles is that they need to be shared and they need to be electrified. Otherwise, it will cause bigger environmental burdens than the current fossil alternatives that we have in place. So I would say to focus on the optimal usage of that technology so that you can decrease the energy use more than focusing on the costs would be a nice idea in that context.
Then we have another question. Several cities in China, including Shenzhen, are exclusively using battery-powered electric buses for their public transport needs.
Mm-hmm.
What do you believe needs to happen to get the major cities in Sweden to do the same?
So the planning processes in Sweden take more time, and I don't find it wrong because you need to be able to be aware of the choices you make and how they can impact you long-term in the future. The difference of China is the size, where we're talking about Shenzhen and we're talking about 11,000 buses that are operating in the city. We're talking about very large deliveries. So the economies of scale are totally different than compared to what we have. But meanwhile, it's important, as I said, to make the right decisions along the way, to use the proper technologies, the proper vehicles, and the proper materials for that usage. So it is easier to electrify with buses that have very large batteries. It is much easier. But it has a very big environmental burden and the life cycle impact of those batteries. You have costs that might be associated with the fact that you need to change that huge battery. And actually the Shenzhen case has shown that you need to change it every 4 years or something, which might be a very big cost. So I think it needs some thought on the technologies that are in place. And for some places it takes more time, for other places it takes less time. Of course, Shenzhen's example is a case where you have the large network to operate and you have the manufacturer in place ready to provide. So it was a success case, and I think we can be inspired from that, but take our time to plan accordingly.
Thanks.
you mentioned the size of the batteries compared to environmental impact. Are there any research that can show where the
if there's a
optimal
source?
solution are? I mean, where the size of batteries compared and the environmental
Yes,
impact
there
are.
is actually, and I have written it. It's this article here. It's under review, but it's part of my thesis, so it will be presented at the defense. There, I looked together with my co-authors on the impact of battery size and different fuels on the bus network of Stockholm. And what I said, that there is an optimal solution between battery capacity and emissions, is what is shown there. So there is. Yes?
Yeah. You also mentioned that in order to get most out of it, it would be wise to place this infrastructure in huge bus hubs. If we think about somewhere like Sollentuna, where 5-10 buses simultaneously stay at the same time, in that case, would the infrastructure coupling with just one bus, or will it be possible for the same infrastructure to charge several buses at the same time?
Yes, there is a lot of different approaches to that and terminal solutions. Some of the solutions available, I haven't seen sharing more than a couple, maybe two each, that you can link two buses at the same time to charge. What you need to think is that if you have one charger that has multiple outlets and you want to charge fast, you will have to split your power effect. So if your connection to the grid was, let's say, 500 kilowatts, it might be a bit higher, but still, and you have 5 buses, you will need to charge with 100 kilowatts max. So you're not utilizing your fast charger to the best of it. It's better to split.
Depending on the cost as well. Depending on the cost side as well.
Yes, totally. To the connection costs.
In the model that you made of Stockholm with the charging points and the average charging time, is the strategy to only charge at the end stations for each bus line, or do they charge during the route as well?
Yes, there is also mid-route charging, but this happens only in hubs.
Okay.
Like the only stations that are selected for mid-route are, for example, if they go at Estra, start of the route, but no one goes on or off the bus there. Yeah. So it is assumed that there will be some time because more passengers get in and out.
Okay.
So mid-route charging is included, and I think it is key for actually getting that little extra energy to go along the route.
In this project, have you also had a chance to get a feedback from the passengers? For instance, there are some who are thinking that instead of using public transport, which is using diesels, it might be better to have their own electric vehicles to use for the job or their daily usage. But in this kind of projects, it will become even more environment friendly. But will it change car ownership a lot, or preference towards public transport, do you think?
I am not working on that field that much, so we did some surveys, but I'm not the one that ran them, so I don't want to say something that is not correct there. What I know in general of that field is that there is generally more appreciation of the electric bus service because it's more quiet and because it's environmentally friendly. I do not know how far the appreciation would take someone from switching to a private mode of transport to a bus. I think it's more important that you have the bus there all the time. So accessibility, high functionality of the system, trips that are often cheap system would be naturally valued more for abandoning private ownership of cars. But it's one very good factor that can be placed among the rest of the factors that will make someone to choose, and it's something that has been one big investment of the Stockholm region for a long time, even before the electric buses. We are almost fossil free now. It's just the extra step that is needed. Yes.
Thank you very much for your talk. Short question, I might have missed it. How long was the Södertälje bus running in the system overall, and are there any? I'm talking about years.
So the Södertälje bus was in operation officially within the project from January 2017, I think, to December? Yes, I think, yes. When the project finished, the operation finished, basically. I don't know if it's still going on now. No?
The bus line is closed.
Yeah, so the bus line is closed. The issue is that it was also a kind of test route, so it was very closely linked to the project as a project in time. We got a year of operation, and that is a very key issue that you're touching upon, the duration of these projects, because we are discussing, for example, the life cycle of the batteries under assumptions that are mostly in some few months or a year or two maximum. We have not seen what happens under log usage. So now what I see is that battery guarantees and operation guarantees are like super key for the market, because we need to know more and we need longer operations and we need more data, more projects. I'm totally agreeing to that. Yeah. Yes?
What were the power ratings for the 3.5 minute charging system, and what percentage capacity of the battery did it charge? Was it like 20 to 80% or what?
It was 20 to 90. So we kept a state of charge that was, and a depth of discharge that was 70% for the battery health. So the battery level was never below 20% and never above 90. And the power was 300 kilowatts for that, which is something that I think with the current developments is quite reasonable to assume. We have like 600 kilowatt chargers now being tested, so.
Do you have other companies like energy companies or others that have their own models on how to optimize these kind of systems, or is the research that you've done, is it the first that you know of?
The infrastructure placement problem has been addressed in the literature quite a lot, but most of the studies have been on private cars, which is a totally different approach because you don't have fixed routes and you don't have to keep schedules. Yeah. On buses, it is the largest that I've seen in number of routes and automatization, and the fact that it uses mid-route stops. So what I've seen in literature is usually less routes and charging. Yeah. So there is no selection of other stops. So yes, there is research on linking the individual lines calculation tools, let's say, to operation tools from the transport companies. So that is going on in Sweden, but that is not a system solution. It's a one-by-one line solution. Yes?
What were the challenges you mentioned with the stakeholders? What can you give any example? Was it talking about technological part or costs, or so what was the challenges between the stakeholders?
There were some open answers to that survey that I can remember some indications. It was mostly on how much time the project took to set in place. There were legal requirements, things missing from the original application for the funding that needed to come back during project operation because they were unclear. And the cost sharing, for sure, but that was not something unexpected, I think, the cost part. But the total project management and how the stakeholders would collaborate in that was the unexpected. And I think that was something that has been happening in a lot of projects, that perhaps you need some preparation stages before starting the demonstration, or you have to have fixed or some set constellations that are ready to go in. I think that the more projects we have, the more these constellations form now. So I don't know if this question would actually have the same answers now. I'm not sure, but might be. Yes.
You mentioned that the secondary coil for the inductive charging weighs several tons. The primary coil.
Yeah.
Is the secondary coil, what sort of weight is that, and does that have a detrimental impact on the bus efficiency?
I don't know how heavy it was. Does anybody know?
If I remember correctly, I think 300 kilos, something like that.
No.
So the Scania people know better that information. I don't know. if it had some impact, or other factors played more impact in the operation than that. If there are no more questions, should we close the session?
Yes, because time is up. So thank you very much for
Thank you. Thank you. Thank you.
And if you haven't had coffee and